This video introduces our ECCV work, Pairwise distance distillation for unsupervised real-world image superresolution. A common way to solve real-world superresolution is to train the model with an extensive input degradation space. Such a model we can call it the generalist, as it can handle diverse input degradation. In contrast, if we train the model with a specific type of degradation, such as only optimize the model for the bicubic downsample low-resolution image, we will obtain a specialist. If we compare the model predictions of them for the bicubic input and the real-world input, such as the photo captured by the Canon camera, we will have different observations. For the predictions from the generalist, none of them have high image quality, but there is a very small gap in the qualities of bicubic and real-world predictions. For the predictions from the specialist, the bicubic input can be reconstructed to a very high-quality image, but there is a large gap in the qualities of the bicubic and real-world predictions. Our motivation is to combine the advantages of the pre-trained generalist and specialist so that we can obtain the high-quality predictions for a target real-world domain. To achieve this aim, we derive a pairwise distance distillation method to complete the unsupervised learning for target real-world data. The main idea of our method is to distill the intramodal relationship of the generalist to the bicubic specialist. Specifically, if we represent the model predictions in a feature space, where the feature space is mainly represented by two directions, one direction is a semantic, the other direction is a low-level characteristic, which represents the statistical feature related to the image quality. Then for the generalist, the prediction from it have similar low-level characteristic because of the small gap in their predictions quality, although the semantics are different for each input samples. For the specialist, the semantic information are not changed by the SR model, but the low-level characteristics are different because that they have higher image quality. To achieve our aim, we first make it the assumption that the specialist also have small gap in its predictions in terms of the image quality. Then we can derive two consistencies. The first consistency lies in the intramodal distance. If we look at the prediction for the same pair of real-world and bicubic input, we can see that the intramodal distance represents the semantic information, which should not be changed across models. The second consistency lies in the intermodal distance. For the predictions of the same input, the difference represents the low-level characteristic shift only, and this difference should not be changed across the input samples. Based on these two consistencies, we formulate our pairwise distance distillation method. Basically, we project the model predictions into the VGG feature space and represent the two consistencies as two regularizations, R-intro and R-inter. Specifically, for the R-inter, we use a gram matrix to calculate the channel correlation between the feature distance. This is to focus more on the statistic information but not the spatial arrangement. The gradient are used to update the parameter of the specialist. At the same time, we also add the supervised loss on the label data. This is to prevent the overfitting to the distillation loss, while at the same time to preserve the high-quality prediction for the bicubic input. Our method as a learning framework can be applied to off-the-shelf pre-trained SR models. Quantitatively, we can improve the performance of the pre-trained model towards the specific target real-world domain. And qualitatively, our methods show a great improvement in the clearness of the reconstructed patterns and the remove of the blur effect. Thanks for your listening. Welcome to check our code and the homepage of our lab.